All right. Hi, physiology students. Well, the university has notified us that because of freezing rain Thursday evening and an anticipated Friday morning, they have recommended if you're capable of giving a lecture online to please do so. So I'm recording Friday's lecture. We don't have much to cover in chapter 2, part 1, cell metabolism. So let's go ahead and get started. So last time on Wednesday, we basically started lipid metabolism and the making of lipids. That's called lipogenesis. So I am going to get my pen here. I should be ready. All right. And this is where we left off on Wednesday's lecture on the 19th. But we talked about when the body has excess glucose above and beyond what it needs, it will take that glucose and store it as fat for times when the body needs that resource. Okay, so what happens is the glucose enters glycolysis to produce pyruvate. Pyruvate goes through pyruvate conversion to make acetyl-CoA. And then the liver uses acetyl-CoA to make fat. Okay, so that fat, get pen, is going to include cholesterol. Cholesterol makes up your cell walls. Cholesterol, it's used to make steroid hormones. And if you have too much cholesterol in your blood, that can actually lead to heart disease and the occluding or blocking of your arteries with cholesterol plaques. And so since we know in the PD that the top three, cardiovascular disease, high blood pressure, and diabetes, that is certainly one of the big three. Okay, so here's where I'm going to start to make some notes. So cholesterol, change the pen. Okay, cholesterol is used for cell membranes. That's our phospholipid bilayer, and to make steroid hormones. Those are hormones like estrogen, testosterone, progesterone. Now, acetyl-CoA is also used to make ketones, which are fat, which can be used to make energy. I'll say to make ATP. And we'll talk about that a little bit more on the next slides. And lastly, acetyl-CoA is used to make fatty acids. So fatty acids are converted into stored fat, which is called triglycerides. That's an E. Okay, so up here, triglycerides, that is the stored fat that we have underneath our muscles, above our muscles, underneath our skin. It's also, you can find stored fat in certain organs like the heart. And so all of these are a storage form of fats that the body can use for energy if it needs to. Now, if you need to make energy and you don't have carbohydrates, then you want to break down lipids and release those lipids into the bloodstream, and then cells can use those lipids to make ATP. The process by which lipids are broken down is known as lipolysis. Lipo is lipids, and lysis means to break apart. Okay, so here's the steps of lipolysis. It's basically going to be the backwards process of making lipids. So if we go back to making lipids, you take extra glucose, okay? Extra glucose is converted into pyruvate. Pyruvate becomes acetyl-CoA, and then acetyl-CoA leads to fats. So in lipolysis, obviously fats are going to go backwards into acetyl-CoA and then into pyruvate. Okay, so the first step is the stored fat, triglycerides. That's the white fat that's under your skin. That can be turned into ketones, and by the process by which the body turns triglycerides into ketones, that's called ketogenesis. So keto is for ketone, and genesis means to make. Okay, so making ketones is ketogenesis. Now, when the ketones are spilled into the bloodstream for cells to use to make ATP, when carbohydrates are absent, that is called ketosis. Okay, Ketosis is using ketones for energy. Okay. Now, in addition to making ketones, triglycerides can be turned into fatty acids. Fatty acids can enter the bloodstream and the cells can take in fatty acids. And then they can take that, convert it back into acetyl-CoA, and then back into pyruvate. Or it could take the acetyl-CoA and jump right into the Krebs cycle to make hydrogen ions. And then the hydrogen ions can enter the electron transport chain, and you've got ATP. So that is how fats are broken down and can be used for energy. So I made it clear on Wednesday, but for people who weren't there on Wednesday, that if a chemical reaction can occur in one direction, it can go backwards into the earlier products, okay? So lipids, the acetyl-CoA can be converted back into pyruvate, and then if you go backwards through pyruvate, back up through glycolysis, that makes glucose, okay? So let's do a quick review. So the chemical equation is glucose goes through glycolysis to make pyruvate, okay? And then pyruvate gets converted into acetyl-CoA. So that was what we learned earlier in lecture on Wednesday, okay? We learned that process and then further. So what happens is if you can go in one direction, here to here, you can go, the body cells can go backwards quite easily. That's what metabolism is all about. It's going in two different directions. So this is how pyruvate can go backwards through glycolysis to make glucose. That's called gluconeogenesis. That was a term that was introduced on Wednesday. So gluco is for the glucose. Neo means novel, like new, and genesis means create. So if you go backwards, it's the creation of glucose from a novel source, a non-carbohydrate source. And then in skeletal muscle and the liver, glucose can be stitched together by glycogen synthase. And that's a process of making glycogen called glycogenesis. Okay, you can even see the word glycogen in it. Okay, so the body doesn't waste anything. If it's using lipids for energy, it can make ketones, it can make fatty acids, those can be in the blood, the cells can use them for energy, or you can take those fats, go through gluconeogenesis to make glucose, and then take that and make glycogen. So these are all chemical pathways. Okay, so let's discuss ketones a little bit more. So on Wednesday and on the previous week, I talked about how when the body is not getting enough carbohydrates, that's what people who are trying to go through ketosis experience. Your body will break down fats in lipolysis and release ketones into the blood, and the cells will use that for energy. So ketogenesis is the making of ketones. Okay, sorry about that phone call. The making of ketones. Ketosis is using ketones for energy. All right, and that's when it's in the bloodstream and the cells are using. So if you click here when you're looking at the online PowerPoint, okay, ketones can be used for energy by many organs, are found in the blood under normal conditions, but not high conditions. If you're fasting, skipping meals, you're not getting enough carbohydrates. If you have badly managed diabetes, you're not managing blood glucose very well, okay? And so the body turns to fat stores and liberates ketones and fatty acids from fat cells in the liver. Abnormally high amounts of ketone in the blood is ketosis. Now, ketosis is not good, all right, we'll get back out of that, because it causes your blood to become acidic. Ketones are acidic. So ketoacidosis is the drop in blood pH from ketosis. And this is not good. Long term, this is not a healthy thing to happen to the body. Metabolic acidosis is metabolizing any molecules that cause the blood pH to drop. I'll just say metabolizing molecules that decrease blood pH. Okay, if it's got the word acid in it, it's going to drop your blood pH. So ketones are acidic. They cause a drop in blood pH, specifically known as ketoacidosis. Fatty acids high in your blood can acidify your blood. Lactic acid in high levels can acidify your blood. And when we metabolize proteins or amino acids and it's high in your blood, that can cause metabolic acidosis. Okay, so when you're online or looking at the online syllabus, if you click here, it's going to give you, I'll make it bigger so you can see it, the lipogenesis pathway. And by practicing this, extra glucose converted to pyruvate, then to acetyl-CoA, then acetyl-CoA is converted into cholesterol, ketones, and fatty acids. And then fatty acids become stored fat. Lipolysis is simply if you go backwards from triglycerides to fatty acids and ketones, and then you can use that, or cells can use that to make acetyl-CoA, which enters the Krebs cycle, which produces hydrogen ions to enter the electron transport chain and make energy. And furthermore, if you go backwards through pyruvate conversion, acetyl-CoA becomes pyruvate. Pyruvate can go backwards through glycolysis to make glucose. Now we've made glucose from a non-carbohydrate source. That's called gluconeogenesis. Okay, so returning to the PowerPoint, because there's not much left to this chapter, amino acid metabolism. So this is when the body metabolizes proteins, and the smallest form of protein is an amino acid. So essential amino acids are ones that we must consume in our diet because our body can't make it. Non-essential amino acids are the ones our body can make. Now, if there are above and beyond the normal level of amino acids in the blood, the liver is going to metabolize that because amino acids cause the blood pH to drop. So what the liver can do to protect the body from this metabolic acidosis is amino acids get converted into pyruvate. Hey, and once you've got pyruvate, you can convert it into acetyl-CoA. It jumps into the Krebs cycle, pumps out a bunch of hydrogen ions, enter the electron transport chain, and you've got ATP. Okay. Now, another thing that can happen is once you've got pyruvate, you can go backwards through lipogenesis. All right. So you can make fat from it. So you can take pyruvate, convert it into acetyl-CoA in your fat cells in your liver. The acetyl-CoA is used to make cholesterol, ketones, and fatty acids. And that is then converted into stored fat or triglycerides. So that's lipogenesis. Now, once you've got pyruvate, the liver does by metabolizing amino acids, you can go backwards through glycolysis and make glucose. And that's known as gluconeogenesis. So the liver is taking excess amino acids that can drop your blood pH, and it's changing it into fat, and it's changing it into glucose, and it's protecting your body from metabolic acidosis. And then if there's above and beyond what the liver can handle and make into fats and make into glucose, it's going to convert the amino acids into urea, and that urea is in your bloodstream now, and that goes down to your kidneys where it gets filtered out and excreted in your urine as ammonia. All right, so it's a waste product, and the body's getting rid of it. Now, blood urea nitrogen, or BUN, there's normal values for that, just like everything in nursing, right? And measuring BUN in the blood can help determine if someone's kidneys are functioning correctly. So there's a normal range for blood urea nitrogen, and anything higher than that is called azotemia. And it can indicate that there's too many amino acids in someone's body, or that their kidneys aren't excreting it as ammonia. Okay, it could also indicate liver problems. So continuing on, I've got a flow diagram for amino acid metabolism. So what the liver can do is it can take amino acids, convert them into pyruvate. So the question is, how can pyruvate be used to make ATP? Here's the answer. Pyruvate is converted to acetyl-CoA through pyruvate conversion. Acetyl-CoA enters, I'll just put Krebs cycle, to make hydrogen ions. I'll just put this. And then you have the electron transport chain to make ATP. Okay, I'm not going to write the whole process out. So that's how it can be used to make ATP, because once you've got pyruvate, you just go through the rest of the process if oxygen is present. Now, what else can the liver convert pyruvate to that can be useful? Fats and glucose. Okay, and by making fats, that's lipogenesis. And by using pyruvate to make glucose, remember it goes backwards through glycolysis, that's called gluconeogenesis. Okay, and we've only got one more slide to go. Okay, so I had the answers. Okay, now let's think. What molecules can the body metabolize that can lead to a drop in blood pH or metabolic acidosis? First of all, think of all the things that end in the word acid. All right, I don't think I have the answers. Nope, so let's think of it. How about what your skeletal muscles produce? Lactic acid. That can drop your blood pH. What about in making of lipids or breaking them down, fatty acids? Okay, remember the body, the liver will release fatty acids into the blood if there's no carbohydrates available. What about what we just talked about? Amino acids. Okay, if it has the word acid in it, it can drop blood pH. And then after that, still considered a fat, but ketones are acidic molecules. And if there's lots of them in your blood, you will have ketoacidosis, which is not good for your body. Last slide. So just to kind of give a clinical application of amino acid metabolism and when it goes wrong, phenylketonuria, that's a mouthful, so PKU. That is, I'm going to click on the app here, make it bigger. It's a genetic condition, okay? And in this disease, people who have it, they cannot break down the amino acid known as phenylalanine. If they consume phenylalanine in food or liquid, their body lacks the enzyme to break that down. So that's the problem, okay? And as a result, the phenylalanine is turned into phenylketones, and phenylketones are toxic to the body. All right, so people who have PKU find out early in childhood. So it's a genetic condition where there is a mutation in the enzyme phenylalanine hydrolase. So there's the ASE, that means enzyme. Hydro means it breaks apart the amino acid phenylalanine. So if you don't have PAH, you can't metabolize phenylalanine, the amino acid. And the body will convert that amino acid into phenylketones, and that comes out in the urine. Now, the phenylketones are toxic, can cause seizures, mental retardation in children. So it's very important for people with PKU to restrict the amino acid phenylalanine in their diet. And since it's so dangerous, if you look at the back of most products you buy in the grocery store, they will have a warning, dietary warning, and they say, people with phenylketonuria, warning, this product contains phenylalanine, so don't consume it. Okay. All right. So this, my friends, ends the chapter on metabolism. The next one we're going to cover is going to be chapter 2, part 2, cell transport. Okay. So from here, keep those notes and I'll be posting them. And then we can back out of here and leave Friday's discussion. So I hope that you stay warm on this cold Friday that we're going to have. And if you have any questions, simply email me over the weekend, and hopefully I'll be seeing you on Monday.